When we analyze a linear operator, we're essentially asking if it can be dismantled. Can we take a complex transformation and break it into independent, untangled pieces? So far in Chapter 7, we've used cyclic subspaces, the rational form and the Jordan form, to segment an operator's action. While these methods differ, they share a singular objective: identifying the invariant factors, the underlying building blocks dictating the operator's behavior. But there is a limit to how far this reduction can go. If we want a system where every single component is independent and nothing is left tangled, we need to look at a property called semi-simplicity. Geometrically, an operator is semi-simple if every invariant subspace has a complementary invariant subspace. We express this separation as a direct sum, decomposing space V into independent subspaces, W1 through Wk. With no tangled components, the operator's action distributes entirely among these distinct pieces.
By ensuring every piece has a complement, geometric semi-simplicity allows us to treat a complex transformation as a collection of smaller, independent, and highly predictable systems. In practice, we can't always hunt for every possible subspace to see if it has a complement. We need a way to verify semi-simplicity using only the operator's polynomial properties. Theorem 11 provides that criteria. It states that an operator is semi-simple if and only if its minimal polynomial is a product of distinct irreducible polynomials. For example, consider a minimal polynomial p of x equals x minus 2 times x minus 3. Because the factors x minus 2 and x minus 3 are both linear and distinct, this operator satisfies the theorem and is semi-simple. Now consider p of x equals x squared plus 1 over the real numbers. This is a rotation operator. Geometrically, it looks rigid because it doesn't leave any lines or one-dimensional subspaces fixed. It moves every vector off its original path. Even though we can't find simple fixed lines here, the polynomial is still a single irreducible factor. Because it isn't repeated, there's no squared term, Theorem 11 tells us that this rotation is still semi-simple. The algebra identifies a clean structure, even when the geometry doesn't offer an obvious way to break it down. Everything becomes even clearer when we move to the complex number field. In this context, every irreducible polynomial is just a simple linear factor. This leads to a major conclusion. Over the complex numbers, being semi-simple is exactly the same as being diagonalizable. If we look at the Jordan form, a semi-simple operator has 0 nilpotent parts. That means those extra ones sitting off the main diagonal simply vanish, leaving us with independent one-by-one blocks. This is why Theorem 13 is so useful. Even if an operator isn't semi-simple, we can always split it into a semi-simple part, S, and a nilpotent part, N, that commute with each other. By separating these out, we can see that the nilpotent parts are the actual source of complexity. They're the components that prevent the operator from being fully dismantled. Let's test this. Look at the minimal polynomial p of x equals x minus 4 squared times x minus 1. Based on what we've covered, is this operator semi-simple? The answer is no. Because of that squared term, the root is repeated. This repetition forces a nilpotent component into the operator, which means we'll have a Jordan block larger than 1 by 1. To summarize, semi-simple operators follow 3 rules. They are completely reducible, they are always diagonalizable over the complex numbers, and they contain 0 nilpotent parts. Understanding semi-simplicity allows you to strip away the complex noise of an operator to see the independent actions underneath. For more deep dives into Hoffman and Kunze, make sure to subscribe.